Hi everyone. So this video is necessary for us to start developing the concept of a confidence interval to estimate a true mean. So this is a bit of an excursion, but we're going to develop an idea called the t-distribution, and I'm going to start by showing you why it's necessary. So we've been working with proportions where we had some kind of estimate, and then we added and subtracted a margin of error, and there were two pieces to that margin of error, and they looked like this. So the two pieces of the margin of error were one, a z statistic, so a critical value that told us how many standard deviations we have to add or subtract to the estimate in order to get a reasonable margin of error. So let's just write that down. Okay, and then the next pieces, of course, are estimated standard deviation, which we call the standard error of the sample proportion, how much the sample proportion is expected to vary in repeated sampling. So I'm going to break that apart a little bit and just remind us where that statistic is coming from. So that z statistic is coming from what we call our standard normal distribution, where we think about a confidence interval or confidence level. We might call it C percentage, right? And then the Z star marks a certain number of standard deviations above or below the mean. And we've been working this out by saying, okay, well, we'll take 1 minus C, the C percentage, and divide it by 2 to get that area. And then we have our Z star, and then we know how many of these standard errors to add or subtract. And remember, that's coming from the standard normal distribution. Let's take a look at now, what do we think the confidence interval to estimate a mean would be? Just gotta fix this. Okay, so we're trying to estimate the true mean SAT score for students in Western Massachusetts or something like that. What would we put into this confidence interval? We would take a sample mean, and we would need to add and subtract some kind of margin of error. So remember, that margin of error needs to include a number of standard deviations and some measurement of the standard deviation. So here's our estimate. And then we'd have to add or subtract how many SD, and I'm going to call it SE for standard error, and you'll see why in just a minute. So this margin of error has the two pieces. The other piece is the estimated standard deviation, which we are going to call the standard error. So remember, before we would say standard deviation of sample means is sigma over square root of n. Well, we do not know sigma when we are doing confidence intervals. If we knew it, then we probably wouldn't be in a situation where we have to estimate something. So like we did with proportions, we're going to estimate the standard deviation, where usually it's just called standard deviation of X, or sometimes it's just S, but I'll just have it refer to the standard deviation of the sample over the square root of n. Okay, so instead of taking the standard deviation of the whole population, we're estimating the standard deviation of the population with a sample standard deviation. Okay. Okay, so then this whole thing, let's do a little bit of side work here. This whole thing would give us standard deviation of sample means, or the sample mean, I'll call it the sample mean. It's a variable that varies in repeated sampling, where unknown, the population standard deviation would have to be known in order for us to calculate that. Here's a new thing, standard error of the sample mean. And this whole thing is now the estimated standard deviation of sample mean. How much we estimate that the sample mean, how much we estimate that the sample mean varies in repeated sampling, where this is a sample standard deviation. Okay, so it turns out that this difference, the difference between knowing the standard deviation of the population and estimating the standard deviation of the population with the sample standard deviation, it adds more variability overall. Okay, so instead of then using a z statistic here, we're going to be using something called a t statistics, t star. Okay, so the t statistic, and there's a little df next to it, which I will explain in a minute. Okay, so the t statistic is something that varies based on repeated sampling. Okay, so a t statistic would be a lot like a z statistic, but let's say we're calculating it for the sample mean. We have the sample mean, we would be subtracting the true mean, and this would all be divided by the standard error of sample means. Let's compare this to a t statistic, or a z. Compare it to a z statistic, where t, or z is sample mean minus true mean over the actual standard deviation of sample means. Okay, so why did I make this one flatter? Well, let's say I have a small sample size. Let's say I have a sample size of, I don't know, maybe just 10. If the sample size is small, then this whole number, this variability in the sample mean, is going to be much more variable. Okay, so there's more variability when the sample size is smaller. And we come to something called the degrees of freedom. And degrees of freedom are n minus 1. So if this were the case, if we had a sample size of 10, then the degrees of freedom would be equal to 1. As the sample size increases, this distribution of t statistics becomes more and more like a normal distribution because there's less variability coming from this extra thing that we have to estimate, right? So when we estimate the standard deviation, we estimate the variability in the sample mean, we get things that are much more spread out. So we have to use a different reference. So these are t statistics. They have a mean of 0, right? Just like z. But we kind of have to allow for more deviation because of that extra variability. So with smaller sample sizes, we might see more deviation above and below the mean. Okay, and then here we have our standard normal. Right, these are t's, these are z's. And these are always the same. Okay, so just keep in mind the difference between z and t. Z has a known population standard deviation and therefore a known standard deviation of sample means. T has an unknown population standard deviation, so it's estimated. So the t statistics are more variable the smaller our sample size is. Okay. There's a lot more to this than what I've just gone over, but what we need to be able to do is look up a t statistic. So a t statistic comes from a table called table B, which I'll show you how to use quickly. And we'll obviously end up using our calculator quite a bit more for this. But basically, I want to look at a situation where, say, I have a sample size, a given sample size of 10, then the degrees of freedom would have to be equal to 9. So I know I'm going to have to look over here. And then I can scroll down to the bottom and find the confidence level that I want. So the confidence level is basically how we know what a confidence level is, right? How sure we want to be that we're capturing the truth in the interval. So we always start with the 95% confidence interval, and notice down here at the bottom we have infinity. So all of these statistics should look like z-scores, because if the sample size is infinite, the t distribution becomes exactly like the z distribution. Okay, basically that's because if we have an infinite sample size, then the sample standard deviation is going to equal the population standard deviation. And also notice that if the sample size is 1,000, these statistics are very, very close. So 1.96 is close to 2, right? That's the number of standard deviations we add and subtract to create our margin of error. But then let's go up in this column, right? And notice that our tail probability is here. That matches the 95% confidence level because it leaves 0.025 probability on either side. So I'm finding this this value. So this value right here is a t statistic. So for a 95% confidence interval, for a mean, would take an estimate and it would add and subtract this many standard deviations above and below the mean. Okay? I'm sure this feels a little shaky at this point. But we should kind of get the overall concept. So T star, we can look up, or we could do inverse T and its absolute value, 1 minus confidence level over 2. All right, so I would go to inverse norm, or second vars, and inverse t, and I'm going to have to plug in some additional information. I hit the wrong one. Inverse t. Okay. This calculator doesn't want to listen to me now. So let's try it again. There we go. So I'm going to do a 95% confidence interval. So I plug in 0.025. And then I always need some degrees of freedom, which are the sample size minus 1. Seems simple. Why is it sample size minus 1? There's a huge long explanation for that, which I can try to explain to you, but for now we'll just go with this. Okay? So this inverse t should give me the same thing that I saw in the table, 2.26. Okay, so then that goes into our confidence interval to estimate a true mean. So that's the t distribution in a nutshell. The next video will show an example of how we do a confidence interval to estimate a true mean.